welcome to CMOS RF integrated circuits. This is going to be the third module. We are going to start the third module on passive components. Today's lecture I will try to cover resistors, capacitors and if possible more. Okay. What are the different passive components? What is passive? Passive is something, first of all, it does not need a power supply. Okay. Mostly these components are linear as well. Under passive components, we have resistors, capacitors, inductors, mutual inductances, even transformers. There is one more new thing over here, and these are wires. I am going to treat wires as components. Let us basically study the wires as well. And in addition, you might also consider diodes as passive components. We are not going to study diodes here in this module. Not passive components, active components. These are transistors. So, these could be MOS transistors, BJT transistors, JFET, whatever you want over here, right. So, these are passive and active components. We are going to study in this module R, C, inductors, mutual inductances, wires, and we will not study diodes. We will take it up later on. Okay. So, first resistors. How do you make a resistor on an integrated circuit? Not all integrated circuit technologies directly offer resistors, but most RF processors do offer resistors. So, modern resistors are made out of polysilicon, a material called polysilicon, the same material which is used for the gate of MOS transistor is also used to build resistors. You can also use metal to make a resistor. In any case, let's just see what is done. So, this is what is done. A track made out of a material which has resistivity rho. I am drawing the top view here. Okay. The side view is like this. Okay. So, these are the side views. It is made out of material which has a resistivity of rho What are the units of resistivity? Yes, what are the units of resistivity? Okay, let us come to the units a little later. It is made out of resistivity rho. It has a cross sectional area A, it has a length L, okay. Height is H, and width is W. So, cross sectional area A is equal to W times H, and let us say you want current to propagate in this direction. Okay. So, in that case I am sure you are familiar with this, the resistance of this track, the resistance R is inversely proportional to A, it is directly proportional to the length, and it is proportional to rho. Okay. So, what are the units of rho? Here we have got ohms, here we have got meters, here we have got meter squared. So, the units of resistivity rho is ohm times meter. Okay. Now, is that fine? So, you will be told by the foundry that the resistivity of the material that you are going to use is so many ohm meters. You can use anything, let us say a piece of metal can also be used to make a resistor. How will you do that? All you need to know is the resistivity of the material and you are done. Okay. Usually we make the resistivity is not enough to make a large enough resistor. I mean, with a track like this we can probably make 100 ohms, we can probably make 200 ohms. If you want 1 kilo ohm, if you basically want a larger resistor, we usually make lot of tracks and put them in a snake like fashion. So, now you have got a resistor between this point and this point, which is 4 times the resistance of each track, assuming the tracks are identical. Okay. If you draw it like this, it is also easy to ratio two resistors. So, if you want R and you want 5 by 4 R, then all you have to do is split R into 4 pieces like I have done for resistor number 1, and for resistor number 2 you use the same piece and make 5 pieces. So, you have got resistor and 5 by 4 times the resistor. Okay. Now, typically the height, this height is defined in the process technology. You have no control over the height. The foundry decides what the height is going to be, right. So, when that is the case, the foundry does not really give you rho, it gives you rho by h, because the height is defined by the foundry. So, what are the units of rho by h? Rho has units of ohm meters, rho by h has units of ohms only, right. Now, it is funny that the foundry tells you that the resistivity is so many ohms. So, it is a little funny to relate ohms over there. They give you a little additional information. They tell you it is so many ohms per square. Okay. Why do they tell you that? Because it is, suppose it is rho prime, the resistance is rho prime times the length divided by the width. So, if I have a track of length L and width W, then how many squares are there in this track? There is 1 square, 2 squares, and then a little more, right. So, the number of squares is L divided by W. So, that is why they usually give the unit as ohms per square, and then whatever the width is, it does not matter, you just count the number of squares in the track and that gives you the resistance of the track. Fine. Okay. This is as much as I am going to talk about resistors. Next, let us start talking about capacitors. Okay. How do you make a capacitance? What is the easiest capacitance you can think of? Yeah? Any ideas? Okay. Two parallel plates. So, whenever you see two parallel plates, anything remotely looking like plates which are parallel to each other, separated by non-conducting dielectric. If they are not separated by a non-conducting dielectric, it does not look like a capacitor anymore, it looks like a resistor or something closer to that, a wire, short circuit. As long as there is a non-conducting dielectric between the two plates, anything remotely looking like plates looks like a capacitor. And what is the capacitance? This is your high school physics. Yes, okay. C is equal to A times epsilon divided by D. So, C is equal to A times epsilon divided by D, that is the capacitance of this parallel plate capacitor. Now, this particular formula which you learnt in your high school is valid for two infinitely large parallel plates. Okay. Otherwise, this formula is an approximation. So, what am I talking about here? You have two plates. How was this derived? Suppose these plates are infinitely large. Okay. They are separated by a distance d, they are infinitely large. You place plus q on the top plate, minus q on the bottom plate, okay. And then you use Gauss's law to find out the electric field in the neighborhood of the capacitor, right. If you put plus q on the top plate, minus q on the bottom plate, where will the charge reside? Will it reside which surface will it reside on? The plus q attracts the minus q attracts the plus q. As a result, all the charge resides on the bottom side of the top plate and the top side of the bottom plate. Okay, that is where all the charge resides. There is no volume charge inside the plate. Okay. Once you understand that, it is easy to compute the field. There is no reason for the field to go here and there. The field will go straight to the field lines will go straight from one plate to the other plate. There is no reason for the field lines to go here and there. Remember, these two parallel plates are infinitely large. Okay. And then once you realize this, you just construct a small Gaussian surface around a piece of charge. So, let us say you construct a Gaussian surface around this charge, it is a surface 3D. Okay. The field lines are all going straight. If the area of the surface is A and the electric field is E, then the total flux, the total area times the field that is coming out is A times E, and that is equal to the charge enclosed divided by epsilon naught. So, let us say this has an area of small a, okay. So, that basically gives you that the field, the electric field is q by a epsilon naught, or where is naught a epsilon, I am sorry. Okay. So, that is the electric field. The distance between the two plates is d. So, the potential difference is the field times the distance. The field is constant. So, it is field times the distance. Okay. And you relate this to your capacitance. So, the capacitance of this object is A epsilon by d. Now, what is the biggest assumption here? The biggest assumption here is that the size of the plates are infinitely large. That makes the field lines perfectly straight. They do not have reason to go anywhere else, they keep coming straight perfectly. These are huge plates. Okay. So, the field lines come straight. Now, if you confine the area, if you say that no, the field the size of the capacitor is not infinitely large, then how are the field lines now going to look? Well, there is going to be something called fringing. So, when you confine this area, the field lines now do not have to go straight anymore, they curve towards the other plate, especially at the edges. This effect is called fringing. You might have heard of this. So, along the border of the area of the capacitor, there is fringing. So, the fringe electric field curves to the other capacitor, right. So, this also I am sure you are familiar with. So, under these circumstances, what do you think is going to be the capacitance of this structure? So, what do you think is going to be the capacitance now? The field line, some field lines are still, most of the field lines are still coming straight down from one plate to the other. they are still coming straight down from one plate to the other, right. They still have more or less the same strength. Some new field lines have come curving from one plate to the other. These are the new field lines, these were not there before. Okay. So, the net capacitance now is proportional to the area, and there is some additional capacitance because of the fringing. Now, this fringing capacitance is going to be proportional to what? Is it going to be proportional to the dielectric constant? Yes. Is it going to be inversely proportional to the distance between the two plates? Yes. What else is it going to be proportional to? Is it going to be proportional to the area? No. Okay. Take a look, or let me draw the top view. So, if this is the top view of the capacitor, there is a top plate, there is a bottom plate, I am looking from the top over here. Fringing happens in this marked area, marked region, only at the borders, that is where the fringing happens. So, what is the extra fringe capacitance going to be proportional to? Yes, the perimeter. So, can my formula look like epsilon times perimeter divided by d? Is it possible? Dimensions. It can't, right? This has dimensions of epsilon, whereas you want dimensions of epsilon times length, a epsilon by d. Instead, you have got perimeter epsilon by d. So, it can't be. So, there has got to be another factor over there which has units of meters. Okay. What else? What else could it be proportional to? Take a look. It is now proportional to the height. Charge will also come onto the sides. Remember, there is no charge in the bulk of the area, but there could be charge on the walls. So, charge will not only reside on the lower wall, the roof, right, the ceiling. Charge will mostly reside on the ceiling, it will also reside on these side walls, right. So, it is also going to be proportional to height, this not height, this thickness. Okay. Now, could this be a formula? Well, the dimensions are right, the proportionality is right intuitively, however, it is not really the case. See, in this case the field lines are curving, they are not coming straight. This would have been correct if they were coming straight. These things, the field lines are curving towards the other plate. So, on top of this there is going to be the effect of the fact that they are curving. So, effective distance between the two plates is more than the distance, right. So, there is going to be some fuzz factor over here. Fine. So, this is the capacitance, that extra capacitance that you get because of fringing. So, if you want to match two capacitors, you want to make sure that two capacitors are equal, then what do you have to do? You have to make sure that their areas are equal, you have to make sure that their perimeters are also equal. Okay. If you want to make one capacitor double the other, then you have to make sure that the area is double as well as the perimeter is double. It is not easy. Okay. It is not easy to make sure that both area and perimeter are double. So, if I have L 1 and W 1, then for the second one this is the area relationship. There also needs to be a perimeter relationship, which basically tells you that L 2 plus W 2 twice of that is equal to twice of L 1 plus W 1. So, you have got two equations, two unknowns, you can solve for L 2 and W 2. There is a unique answer, okay, to do this. So, if you want the relationship, I am sorry, if you want one capacitor to be n times the other capacitor, then there is a unique relationship and it might not be easy to make this, right, but beware. You can also just put two of them, you can put two capacitors each of size A 1 and then you basically get the advantage of both area doubling and perimeter doubling. So, that is also a possible way to do things. Now, how do we make capacitors on an IC? So, what we have learned so far is that the area of the capacitor is important. The field lines now do not have to go straight anymore, they curve towards the other plate, especially at the edges. This effect is called fringing. You might have heard of this. So, along the border of the area of the capacitor, there is fringing. So, the fringe electric field curves to the other capacitor, right. So, this also I am sure you are familiar with. So, under these circumstances, what do you think is going to be the capacitance of the structure? So, what do you think is going to be the capacitance now? The field line, some field lines are still, most of the field lines are still coming straight down from one plate to the other. They are still coming straight down from one plate to the other, right. They still have more or less the same strength. Some new field lines have come curving from one plate to the other. These are the new field lines, these were not there before. Okay. So, the net capacitance now is proportional to the area and there is some additional capacitance because of the fringing. Now, this fringing capacitance is going to be proportional to what? Is it going to be proportional to the dielectric constant? Yes. Is it going to be inversely proportional to the distance between the two plates? Yes. What else is it going to be proportional to? Is it going to be proportional to the area? No. Okay. Take a look, or let me draw the top view. So, if this is the top view of the capacitor, there is a top plate, there is a bottom plate, I am looking from the top over here. Fringing happens in this marked area, marked region, only at the borders, that is where the fringing happens. So, what is the extra fringe capacitance going to be proportional to? Yes, the perimeter. So, can my formula look like epsilon times perimeter divided by d? Is it possible? Dimensions. It can't, right? This has dimensions of epsilon, whereas you want dimensions of epsilon times length, a epsilon by d. Instead, you have got perimeter epsilon by d. So, it can't be. So, there has got to be another factor over there which has units of meters. Okay, what else? What else could it be proportional to? Take a look. It is now proportional to the height. Charge will also come onto the sides. Remember, there is no charge in the bulk of the area, but there could be charge on the walls. So, charge will not only reside on the lower wall, the roof, right, the ceiling. Charge will mostly reside on the ceiling, it will also reside on these side walls, right. So, it is also going to be proportional to height, this not height, this thickness. Okay. Now, could this be a formula? Well, the dimensions are right, the proportionality is right intuitively, however, it is not really the case. See, in this case the field lines are curving, they are not coming straight. This would have been correct if they were coming straight. These things, the field lines are curving towards the other plate. So, on top of this there is going to be the effect of the fact that they are curving. So, effective distance between the two plates is more than the distance, right. So, there is going to be some fuzz factor over here. Fine. So, this is the capacitance, that extra capacitance that you get because of fringing. So, if you want to match two capacitors, you want to make sure that two capacitors are equal, then what do you have to do? You have to make sure that their areas are equal, you have to make sure that their perimeters are also equal. Okay. If you want to make one capacitor double the other, then you have to make sure that the area is double as well as the perimeter is double. It is not easy. Okay. It is not easy to make sure that both area and perimeter are double. So, if I have L1 and W1, then for the second one this is the area relationship. There also needs to be a perimeter relationship, which basically tells you that L2 plus W2 twice of that is equal to twice of L 1 plus W 1. So, you have got two equations, two unknowns, you can solve for L 2 and W 2. There is a unique answer, okay, to do this. So, if you want the relationship, I am sorry, yeah. If you want one capacitor to be n times the other capacitor, then there is a unique relationship, and it might not be easy to make this, right, but beware. You can also just put two of them, you can put two capacitors each of size A 1, and then you get basically get the advantage of both area doubling and perimeter doubling. So, that is also a possible way to do things. Fine. Now, how do we make capacitors on an IC? So, what we have learned so far is that the area of the capacitor is important, the distance between the two plates is important, the perimeter of the capacitor is also important. One more important thing of note over here, when do you think the fringe capacitor is more important than the other A epsilon by d? So, let us say this is the normal capacitance. When is the fringe capacitance more important than the normal capacitance? Look at this. When do you think it is more important than the normal capacitance? When the height, the distance between the two plates is comparable to the length and width of the capacitance. That is when the fringe capacitance becomes very important. If the distance is much smaller than the length and width, then it is like the fringe is really a little bit extra, right. Otherwise, when the length and width are comparable to the distance between the two plates, then the fringe capacitance is going to be huge. All right. So, if I make a wire, suppose I make two wires, okay, and the distance between the two wires is comparable to the width of the wire, then there is going to be huge amount of fringing on the sides. Okay. There is going to be some actually not these sides. So, there is going to be a lot of fringing in this case when you have if you just place two tracks parallel to each other. So, you usually want a large area. Okay. Now, let us start giving you some numbers. We can use the distance between two metal layers on an IC. So, we can use two metal layers on an IC, and these could be the two plates of my capacitor. The distance between the two metal layers is kind of controlled. Distance could be as large as 0.1 microns in your latest 28 nanometer process. It could be as large as 0.1 microns. In little older processes, it could be as big as 1 micron. Let us say you are talking about a 0.13 micron process. The gap between two metal layers could be as large as 1 micron, 1 micrometer. Okay. What is the material in between? What is the material in between two metal layers on an integrated circuit? It is silicon dioxide. Okay. Glass. So, silicon dioxide is a known material that is usually used to insulate all the different metal layers, and it has a known dielectric constant 3.5 or so, and you basically make the area, you create the area on the top metal layer, you create the area on the bottom metal layer, and you have created a capacitor. Okay. Unfortunately, this distance between the two plates is not in your hand, it is in the hands of the foundry. Okay. So, there could be errors in that distance also. So, between process to process, this distance could change, between wafer to wafer this distance could change, and as a result the value of the capacitance will have errors. I mean, it will not be a precise value. Okay, the area is more or less what you want, but the distance need not be what exactly you want. There could also be a gradient in the distance. So, maybe the foundry did not do a terrific job, and these two plates are not exactly parallel to each other, they are tilted. It will still work as a capacitor. So, side view maybe it is going to look like this, I am drawing quite exaggerated. Okay. It will still work as a capacitor. You will now have to think about the median distance between the two plates. That is how it is, you get what you get, can't ask for more. Okay. Now, some of the modern processors, they offer some capacitors called MIM capacitors. Okay. So, these are special capacitors which are offered in the top layers, top metal layers, and they give you these, they have a controlled distance, much lesser distance between the two plates. So, if you want to make a capacitor of 1 picofarad, let us say, if the distance were lesser, you would have used lesser area to make it, am I right? If D is lesser, then the area you need to make the given capacitor is also going to be lesser. So, I would like my foundry to give me two layers as close to each other as possible, that will give me the most area efficient capacitor, right, and area is money in terms of silicon. Okay. So, that is why some foundries they offer two specially created metal layers which have lesser area between them as opposed to two regular metal layers. Okay. You have to pay extra for that. So, I do not know if you are going to gain in terms of money or not effectively. Okay. The other well known capacitor is the gate oxide of a MOSFET. So, can I use the gate oxide of a MOSFET to create a capacitor? This is actually something which is very popular, and the reason behind it is that this gate oxide the thickness of the gate oxide of a MOSFET is well controlled and very small. So, you get extremely high capacitance density and you get a much better controlled value of the capacitance than you would otherwise get if you take 2 metal layers. Okay. So, what you have to do is you have to hook up the MOSFET, you have to make a MOSFET, you have to use the gate of the MOSFET as one plate and the source and drain need to be connected together and they are the other plate together. This will work only when the MOSFET is in strong inversion. So, this will work when the voltage between these two nodes is more than a VT. Okay. Roughly speaking, more than a threshold voltage of the MOSFET, then the MOSFET goes into strong inversion, then there is an inversion layer of charge, basically the second plate, the bottom plate of the capacitor is created only then. Okay. And then you have a nice controlled capacitor between 2 points. Okay. So, the drawback of this is that the advantages are well controlled, much greater density, okay. The disadvantage is that you need more than a VT. Is there any other disadvantage? Yes, there is a second disadvantage. The second disadvantage is the ground plane, right. The bulk of the MOSFET is going to be connected to ground. Suppose this is an N type MOSFET. So, the bulk is connected to ground, it is P type substrate, it is connected to ground, and as a result you get a parasitic capacitance between the top plate and ground. Okay. Basically, you get a parasitic capacitance between the top plate and the bulk, which happens to be the ground. So, if you are planning to make a floating capacitor between 2 points, this is not the way to go, because now unfortunately you are trying to make this. Okay. Unfortunately, you have got some parasitic capacitance from the gate to the substrate. You have also got some parasitic capacitance from the bottom plate to the substrate. So, this is what you have built, and all of these are reasonably, these parasitics are reasonably comparable to the capacitance between the two the floating capacitance basically between the gate and the channel. So, this is a drawback of this technique, right, you agree? Okay. If one of the nodes was ground, if this was indeed ground, then this capacitor does not matter, you have got a little more capacitance than you wanted, than you desired, right. So, we usually make a lot of decoupling capacitors. We usually make a lot of decoupling capacitors where we want large capacitance value, therefore, we want great density, because we do not want to waste huge amounts of area. We also want, in a decoupling capacitor, one side of the capacitor is going to be either ground or a constant fixed potential. In small signal it is ground, fixed potential is ground in the small signal. So, therefore, this kind of a capacitor is advantageous This disadvantage is not there, because you know it is a capacitance to ground. The value of the capacitance is not very critical, because it is a decoupling capacitor. You just want some large massive capacitance over there, and you get great density. You just have to make sure that you have more than a VT between the gate and the drain and source, right. So, this is very routinely used in decoupling capacitors. For other applications, if you want a floating capacitor, beware. Okay. So, if you want a floating capacitor, you can use two metal layers, let us say metal 2 and metal 1. Is this okay? Is this okay? No, it is not, right, because as soon as you use metal 2 and metal 1, you have to remember that there is also a substrate. The substrate is connected to ground, and if you place charge minus q on this plate plus q on the top plate, then a reflection of that charge is also going to appear in the ground plane. Do you remember your electrostatics? You have a surface, you put a point charge plus q, it is going to appear as if there is a minus charge of, there is a reflection charge of minus q somewhere over there, and as a result there are going to be field lines between these two charges. Okay. This method of reflection or something like that. Yeah. Okay. So, if you have any charge on top of a ground plane, on top of a conducting plane, you get an equal and opposite charge beneath the conducting plane. You do not really get that charge over there, it looks as if you have got a piece of charge over there, fine. Now, you put lots of charges, each of those charges will have equivalent reflections, mirror images. You put a sheet of charges, you will get a sheet of charges in the bottom. So, basically you are going to get a capacitance between M1 and the ground plane. Ground plane is a plate, M1 is a plate, you have got a capacitance between M1 and the ground plane, right. So, effectively what you are going to get finally, you have made a floating capacitor between metal 2 and metal 1. There is going to be a parasitic capacitance between M1 and ground. There is also going to be a parasitic capacitance between M2 and ground. Right. So, you got the same old story as before. Did you or did you not get the same old story as before? It is the same thing. Well, it looks the same, it is just that the distance between the gate and the substrate is much lesser than the distance between M1 and the substrate, or between the distance between the channel and the substrate is much lesser than the distance between M1 and the substrate, right. So, these are lesser than earlier, these parasitics are smaller than if we had used a MOSFET. Because they are a little further away. So, the parasitics are smaller, however, they are there. So, beware, they are there, you cannot do anything about them. So, in that case what else can you do? If you want to make a floating capacitor, what should you be doing? Yes, you should be using the top 2 metal layers, not the bottom metal layers. So, if your process offers 8 metal layers, you should be using metal 8 and metal 7 as your 2 capacitors, as your 2 plates of the capacitor. So, metal 7 is presumably much further away from the ground plane as metal 1, metal 8 is much further away from the ground plane than metal 2. So, as a result the parasitics will be much lesser. Okay. If you have equal spacing between all the metal layers, then you have got 4 times lesser parasitic in this case in the top plate and 7 times lesser parasitic in case of the bottom plate, right. So, you have really won by a huge margin. So, the idea is go as far away from the ground plane, as high up as possible from the ground plane. Do not be close to the ground plane, because that is going to create parasitics, right. Okay. What else can you do? Can you use the sides? So, let us say I am now going to talk about metal 1 only. Okay. I am going to draw the top view of metal 1. If I draw a track like this in metal 1 and another track like this, both are in metal 1. Okay. First of all, remind yourself that let us say in a process technology node of 0.13 micron, the spacing between 2 metal layers is 1 micrometer. Okay. Process technology node of 45 nanometers, spacing between 2 metal layers is probably 0.25 microns. So, it is larger, significantly larger spacing between 2 metal layers. But in a process technology of 0.13 micron, when I can make a metal spacing of 1 micron, I can have 0.13 micron over here between the 2 wires, because that is the technology node, that is the trace width, the resolution I have got. So, I can really squeeze the area over there. Okay. What do I gain? What is the capacitance of this? Is this a capacitor? 2 wires parallel to each other? Yes, this is a capacitor. This could be a capacitor. Basically, I have to think of the height of the metal layer also. Now, the area of this is the length of this track times the height. And the gap between the two is basically responsible for the distance between the 2 plates. Is there going to be fringing? Yes, of course, there is going to be huge amounts of fringing, because now the height is very small, right. The area the area has 2 components, width and the length, height and the length. The height is comparable to the width probably, right. So, there is going to be fringing, there is going to be fringing on the over the top and underneath the bottom. Okay. So, make sure that there is fringing, but fringing is not bad, I mean it just adds a component. So, as long as you know the height, you can compute out the fringe factor, the fuzz factor over there, and you can figure out for yourself what is going to be the capacitance value. What is the perimeter here? The perimeter is twice L plus the height of the metal. Okay. So, you can basically put two wires parallel to each other, and that gives you a capacitance. You get your, you will surely get much better capacitance density than before, because you know what, now you can really squeeze down the gap between the two plates. Okay. This is so a lot is in the hands of the foundry. So, the height is in the hands of the foundry, right. Earlier the gap between the two plates was in the hands of the foundry, now the height is in the hands of the foundry. What else? You have to simulate the fuzz factor, right. You have to know what that fuzz factor is. It basically will depend on the geometry. Okay. So, how do capacitors like this look? So, let us say I want to make a capacitor between 1 and 2. Oh, what about parasitics to ground? Both of these will have equal parasitics to ground, right. They are equally far away from the ground plane, whichever layer, metal layer they are in. So, if you use the topmost metal layer, then they have equal parasitics to ground, but you know lesser. So, beware that they have parasitics to ground. As long as you are aware of that, you make your design. In this case, they have equal parasitics to ground. In the earlier cases, metal 2 had less parasitic to ground than metal 1, metal 8 had less parasitic to ground than metal 7. Fine. So, how do capacitors look like finally? Well, you could make a parallel plate capacitor look like that. So, now you get double, you not only get advantage of this interface, you also get advantage of this other interface, right. So, effectively you have even further doubled your capacitance density. Okay. So, these are commonly used techniques. What people further do is, let us say this is metal X, on metal X plus 1 they have another set of these with the opposite configuration. So, now I am going to draw a 3D picture for you. So, I am not sure if it is clear, but so on the higher layer. So, this is metal x plus 1 and this is metal x. Okay. So, on metal x plus 1 you do this fingered capacitor, and on metal x right beneath that you do the exact opposite. So, now not only do you get the side walls for your capacitors, you also get the surface area of the capacitor. So, this is the cross section. So, you not only get this capacitance, you also get this capacitance. Okay. So, we will stop here, we will look at a couple more of capacitor configurations, and we will continue in the next lecture. Okay. Thank you.